Hello friends, Namaste all of you, Namaste everyone, and myself S.S.Takalkar, of course, your friendly teacher. Dear friends, today we are going to solve some problems which are based on the concepts of the different definitions which concern to the enthalpy changes in different processes. So here, as per discussed in the last lecture, we have derived certain formulas here. Delta H is equal to Qp, that is the heat absorbed by the system at constant pressure. Similarly, the heat capacity at constant pressure, molar heat capacity, can be given as number of moles, right, or amount of heat absorbed per mole per degree Celsius. So one can write here delta T. Similarly, the specific heat of the substance can be written as the amount of heat absorbed by 1 gram of the substance. This is in grams. So divided by the mass in grams, whatever are the grams per degree Celsius, that is the rise in the temperature, etc. Now, depending upon certain concepts, we are going to solve these problems, which is a typical problem. Consider, we have to calculate the energy required, that is the energy absorbed during the process in which the water at minus 50 degrees Celsius, that is ice, is heated so as obtain its vapor at 160 degrees Celsius. Okay. Now consider the ice, that is a solid, and it is given at minus 50 degrees Celsius. So if it is heated, one can obtain first H2O, suppose at 0 degrees Celsius, right? Minus 50 degrees Celsius to the 0 degrees Celsius, heating is given. Then at 0 degrees Celsius, there will be a equilibrium between H2O. Here it becomes a liquid now, right? So this process is taking place at 0 degrees Celsius and pressure is 1 atm pressure. So this is nothing but the fusion, FUSH, heat of fusion, enthalpy of fusion in this process. So temperature remains constant here until all the ice is melted. The temperature remains constant, that is 0 degrees Celsius at this pressure. Then again the heat should be continued and the H2O can be obtained up to 100 degrees Celsius, from 0 degrees Celsius. This is of course at 0 degrees Celsius. Both are in equilibrium. Then the heating is going on. It absorbs then again it reach to the temperature 100 degrees Celsius. There exists liquid water and gaseous state water, right, at 100 degrees Celsius. So here this is nothing but the process of the vaporization and the amount of heat absorbed per mole at this constant temperature and constant pressure, that is 100 degrees Celsius. Temperature remains constant. Phase change. This is called as a phase change. Here also phase change. Here there is no phase change. There is an absorption of heat, and it depends upon the material. Here there is a liquid water. Here there is a solid water. Again, we have to go. The last stage is given, that is H2O. It is obtained at 160 degrees Celsius, right? In this way. Okay. So here, consider now from this test the amount of heat absorbed, say Q1, right? it is absorbed the heat. The solid is converted into this H2O solid at 0 degree Celsius from minus 50 degree Celsius. So heat is absorbed. Then again here the Q, right? That is the phase change is taking place, and it is nothing but this enthalpy of fusion. Okay. Again, this is said to be a Q2. Again, here it will be a Q3. Right, here the temperature increases from 0 to 100 degrees Celsius. Again at 100 degrees Celsius, suppose it is a Q4. That is the enthalpy change in the vaporization. Enthalpy of vaporization. So per mole, right, is the amount of energy absorbed here. And again, when this gaseous state of the water at 100 degrees Celsius again is heated, elevated conditions, then this is said to be Q5, that is the amount of heat absorbed by the gaseous state of this water and converted into the 160 degrees Celsius. So how much heat energy that means how much heat energy required when 10 grams of ice, it is given 10 grams ice. Now consider one by one. So what is given here? You have given the things are given here. Given 1 delta F fusion F is equal to 6.01 kilojoules. Okay. Also vaporization F is equal to 40.70 kilojoules per mole, of course, per mole. Also, specific heat of ice is given in grams is given 2.087 joules per gram per degree Celsius. What it means? Specific heat can be defined as the amount of heat absorbed to raise the temperature by 1 degree Celsius for the 1 gram of the substance. Right? Then the specific heat, this is for the ice. Now here the phase change is taking place, and after that this liquid water, its temperature going to increase from 0 degree Celsius to the 100 degree Celsius. Right? So Q3 heat is absorbed to raise the temperature from 0 to 100 degrees Celsius. So here it is the liquid water. So here for the liquid water, the specific heat given is 4.184 joules per gram per degree Celsius. And finally, specific heat for, now here the phase change, that means liquid water is in equilibrium gas. When all the liquid is converted into the gas, then the excess, the heat is absorbed by the gaseous state of water and its temperature rises, and here it will be a vaporized state of the water. Right? So as vapor state or gaseous state, gas H2O. Right? And for this it is 2.00 joules per gram per degree Celsius. Specific heat is given, right, for ice, for liquid water, and for the vaporized state of the water. So what it means? This amount of heat is absorbed in joules per gram per degree Celsius. When 1 degree Celsius temperature increases, then for 1 gram this amount of heat is absorbed by the ice, and in this way it is going to increase. Now consider Q1 is equal to what is Q1? That means the amount of heat absorbed by the ice at minus 50 degrees Celsius to go or convert it into the 0 degree Celsius by the absorption of amount of heat. So here, as per discussed here by the definition, for 1 gram or 1 degree Celsius, this amount of heat is absorbed. Then for this much temperature difference, 0 to minus 50 or minus 50 to 0, this means delta T is 50 degrees Celsius, and for 1 gram is given this. So for 10 gram is the substance, right? So here for 10 grams, for this difference, how much it is absorbed? So the formula discussed as in grams, it is in grams, right? Okay, in grams. Multiplied by the specific heat for the solid. Okay. And temperature difference here minus 50 to 0. That is temperature difference is 0. So we can write here formula. Okay. This is in degree Celsius and this is the joules, right, per gram per degree Celsius. Okay. So how much? 10 gram. One can write here 10 gram into the 2.087, right? This is the joules per gram per degree Celsius multiplied by the temperature difference, that is 50 degrees Celsius. Okay. 50 degrees Celsius. Yes. Okay. I'm going to obtain. So here grams between cancel here. Grams, okay, degree Celsius. Then 50 into 2.0 and 10. Whatever obtained it is in joules. Now consider the Q2. Right. So what is Q2? That is the heat absorbed in the phase change. Phase changes from solid to the liquid. This is nothing but a solid. H2O solid from minus 50 to 0. Phase changes. The amount of heat absorbed in the by 1 mole of the solid, right, at given pressure and temperature, constant pressure and constant temperature, that is called as the enthalpy of the fusion, or here it is given enthalpy fusion. It is in kilojoules per mole is given, right? 4 mole is given. We like to calculate 10 gram is there, 10 grams. So either this 10 gram convert into the moles. How? 10 divided by 18. 10 divided by 18. Right? For the water, it is 0.555. Oh. So number of moles is equal to, that is W upon M. The given mass upon molar mass of the H2O. This is the moles. Or so this can be remains as it is in grams, and this kilojoules can be converted into the joules here. So right here joules. Okay. So here this can be for the 6010 joules per mole, or further per gram. How many per grams are there? So it is divided by 18. 6010 18. So it is the joules per gram. Oh, joules per gram. Oh, one can write here also joules per gram. 18 is the 1 mole of. So similarly here also this is the 4700 joules per mole. Therefore, this can be equal to 47 divided by 18. Whatever it will be the in joules per gram. One can calculate it first. Okay. So it is obtained to be here. One can write here. This must be first write here 22. 61.111 joules per gram. Okay, joules per gram. And it is found to be, this is as is equal to 333.3888 joules per gram. Okay, joules per gram. So consider Q2. So here Q2 in this case phase change. What is this phase change? That is the number of moles or number of grams, right? Then the heat capacity then or enthalpy change in grams, right? So what is it? So it is nothing but 10 gram into delta H here for fusion 333.88. This is in gram 10, right here in gram. This is the amount of heat joules per gram, right? So gram we can cancel, and whatever we obtain is equal to joules. Okay, right. Now consider Q3. What is Q3? That is the heat absorbed when from 0 degree Celsius to the 100 degree Celsius. So here the liquid water is there, and for 10 gram of the substance, let here like the specific gravity for the liquid water and the temperature difference again is considered. So this is equal to 10 gram, right? 10 gram multiplied by the specific gravity 4.184, right? This is a joules per gram, right here, per degree Celsius, multiplied by the temperature difference now from 0 to 100. So here 100 degrees Celsius. Okay. So this is getting cancelled, grams and grams. So whatever answer obtained, we can find here again. Oh. Now Q4. There is Q4 here. The rate change is identical. So what is here? Enthalpy of vaporization can be defined as the amount of heat absorbed per mole of substance, liquid substance, to convert it into a gaseous substate at constant temperature and constant pressure, right? So per mole is given. So here in this case it is obtained already here 40.70 kilojoules per mole. That is the enthalpy, that is the amount of heat absorbed by 1 mole. So it is converted into the per gram, right? 2261. So we can write here the M into delta. Here it is a fusion, right? In terms of fusion, here right here, fusion. It is considered as vaporization. This is equal to 10 grams multiplied by delta V. Here 2261.11. This is the joules per gram, right? So this gram and this gram get cancelled, and what is obtained is 22611. Here, oh, right? Now, then when all the H2O, 10 grams H2O is given here, is converted into the gaseous state at 100 degrees Celsius at equilibrium with water, then further heating utilized to increase the temperature of gaseous water to reach to the 160 degrees Celsius. From 100 to 160 temperature difference is there. So one can write here Q5 is equal to amount of mass into specific heat of the vapor state or gaseous state, specific, and delta T. Okay. So here it is a 10 gram. Okay. Multiplied by specific heat for it is 2.0. Right? Here for the gaseous state of the cell, joules per gram per degree Celsius multiplied by temperature difference from 100 to 60. So 60 degrees Celsius getting cancelled, gram getting cancelled. Then 10 into this 2. Okay, 10 grams into this 2. Wait, into this 6. Okay. So here one can obtain 1200 joules. Okay. Now one can add total heat obtained will be So it is found to be here 10 into 2, 20. So here it is obtained that the Q2 is 1040 joules. Okay? All others are okay. On the addition, one can obtain 32. Now, total heat obtained, total energy or heat energy is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5 is equal to 32,373 point or something, whatever it be, the joules. Okay, so here 32.373 joules is the answer. Okay. That means always there is either question, one question is there on such a concepts, right? So the total problem at a time is not given to you because it is very lengthy, right? So during the exams, NEET or JEE exam generally, any step is considered, or sometimes the diagram is given. I hope, and this is, I think, this is a very important. Which clears the concepts of the definitions. So any step you have to calculate, right? So this is the concept. Now here we have used that is a mass in grams. Sometimes the number of moles are also considered like this in this example. Okay, here either this or this, any one is equal. So depending upon the given problem, one can solve. A same problem can be solved by the second method. We are going to solve during the next time also. Okay. Now continue dear friends, as you study about the different enthalpy changes for different processes, enthalpy changes for the phase transition, or enthalpy changes for ion or molecular changes. So as we discussed yesterday's lecture, one can show as the highlights delta H of different processes. Okay. Some physical changes, then chemical reactions or reaction generally, and delta H can be calculated from using the bond energies. In chemical reaction generally, as you know, delta H, rate of reaction, it may be a combustion reaction, it may be a formation reaction like this, or it may be a standard rate of formation, standard D0 represents standard. So this is the standard heat of formation. F, and this is the enthalpy of fusion, FUS. Okay. Now, also if the reaction is combustion type, right? So standard heat of the combustion or enthalpy, standard enthalpy of combustion. This is the heat of formation or standard enthalpy of formation. What is it mean? Standard, that means In this case, suppose any reaction taking place, suppose A reaction is B moles of B, and C moles, D moles of B are formed, right? Any hypothetical example is considered. Then the heat of the reaction for this reaction is the sum of the enthalpy changes of the products, right? Products. Okay. Products. Yes. There is products. Minus sum of the enthalpies of the reactants. Now, if all these A, B, C and D, all these substances are in their standard states, then these reactants, if these reactants are in their standard states, then the heat of reaction is said to be the heat of formation, but in their standard state. Therefore, standard heat of formation, standard enthalpy change of the reaction, standard is 0 of the reaction. Now, what is mean by standard state? Standard state, that means the state in which the substances are very stable, more stable in their state, that state, condition of temperature and pressure, and it is considered, the temperature is considered as 25 degrees Celsius, right, or 298 degrees Kelvin, right. So this is the temperature is considered standard temperature, SPT, and pressure is considered as 1 bar, or it is 0.987 atm. It is considered approximately equal to 1 atm pressure, right? 1 atm pressure, 1 bar pressure. So any substance at this pressure and this temperature, if the reaction carried out, then whatever change obtained, that is the for 1 mole, right? That is the standard heat enthalpy of formation. Then 1 mole of substance in their standard state obtain the reacts and give the products in the standard states. Now consider. So this is about the reaction. Then one can also, for this reaction, one can also written as delta formation as 0. Standard enthalpy change for this reaction will conclude the products C times the standard enthalpy of the formation of C, right? H for C, right? 0. Then here H 0 T, right? Yeah, capital. Okay. Minus 8 times plus B times. So here the enthalpy change accompanying the reaction for 1 mole of the reactants in their standard state, right? They react in their standard state, that is at this degree Celsius and at this pressure. Okay. So whatever is the enthalpy change called as a standard enthalpy change. Okay. E. Now reaction is combustion type. Combustion reaction. That is the fuel or any substance oxidized, right? Burn in the excess of oxygen, giving a product. Then instead of the formation, one can write the combustion also. Yeah, combustion. C. What it means? The standard heat of combustion. Standard heat of formation. Oh. So here we are going to solve the problems based on this concept, right? That means now one very important thing is that here if we consider molecule, Cl2 molecule, Br2 molecule, or oxygen, etc. Now how it is formed? Hydrogen plus hydrogen giving hydrogen. Right. So what is the standard state? Actually, for the elements, this is the rule. For the elements, very important rule. The elements in their pure state, pure elemental state have the standard enthalpy, that is enthalpy change. Enthalpy change is zero. Very important, right? First, Br2 of course liquid is considered. Otherwise, the standard enthalpy for Br2 in liquid is equal to 0, but Br2 in gaseous state it is not 0, right? It is not 0. Standard enthalpy change. Okay, formation. Okay. So it is about 43 kilojoules per mole. Why it is so? Because this is not a standard state gas. Bromine at 25 degrees Celsius, it is in liquid state. Similarly, oxygen standard enthalpy of formation for the oxygen is equal to 0. But standard enthalpy of the formation of O3 is equal to 143 kilojoules per mole, right? Because this is at 25 degrees Celsius is not formed. When oxygen reacts, O3 forms, so this is the difference between the processes, right? So here, this is also one of the important things. That means substances are considered as their standard state, and all the elemental bonds, that means suppose carbon, single carbon, right? Or any element in its standard metallic state, non-metallic state, the standard enthalpy is said to be a 0 by this definition. Okay, standard enthalpy of the formation for the carbon or any sodium, right? Or any metal or non-metal or the molecules like S2, O2, O4, SN, right? Or they are in pure state elements, right? O2 is there, Br2, Cl2, etc. Elemental state, pure state. They have a 0 standard enthalpy, right, of formation. Standard enthalpy of formation. They are 0 in their elemental, non-elemental state, that is metallic, non-metallic, or the molecules in their elemental state, pure state. The enthalpy of formation is 0. Then suppose H2 plus Cl2 giving twice Cl. Right? Yes. Right. So in this case, it is determined and it is found to be the particular values. Okay. We are going to solve the problems based on the determination of the standard enthalpy of the combustion or standard enthalpy of the formation. Right. So this is about the chemical reactions. Enthalpy changes. Now, very important point. We are going to study the heat of solution. Physical status. Last time some heat change. Similarly, atom or molecular changes we have seen. Okay, so here the enthalpy of ionization or enthalpy of dissociation, that is enthalpy of the atomization, right? Or enthalpy of electron gain and enthalpy of the dilution, and enthalpy of the solution. Very important. We are going to study in details about this because enthalpy of the solution cannot be calculated practically, cannot be determined practically, cannot be measured practically, but it can be determined using this laws. Or one of the example we are going to study with the help of Born-Haber cycle. Now what is the definitions already you studied last time? Ions are all these are said to be 1 mole of the substances, right, in their gaseous state, okay, is converted into the next. Now for example, here you study that is the sodium in gaseous state gives sodium ion plus electron in its gaseous state. So amount of heat absorbed or enthalpy change accompany 1 mole of gaseous substance, right? It may be atom or it may be a ion, like this. And you studied 1150 kilojoules per mole is the amount of heat absorbed here. Here you also studied that 1 mole of sodium atom in its gaseous state when ionizes or means positive ions, the amount of heat absorbed is 496 kilojoules per mole. That is ion. Okay. So here we are going to study in this way the new definition, heat of dilution or enthalpy of the dilution. It is very simple. That is the enthalpy change. Enthalpy change when a solution is diluted from one concentration to the other concentration. For example, if HCl, right, the gas, 50 moles of H2O, right, HCl aqua is formed, and in this case it is found to be 73 kilojoules per mole. Okay, and same HCl gas when excess, then same formula HCl aqueous, it is found that 75 kilojoules per mole heat is equal, right? Heat is what? That means heat of dilution as is equal to dilution. Okay, is equal to minus. This is what. So amount of heat evolved. So this is from one concentration to the other concentration. Excess H2 is there, infinite moles are there. Then some extra heat is evolved, and the difference is said to be about the 2 kilojoules per mole. 2 kilojoules per mole. So here the heat of solution we are going to discuss during the next lecture. Heat of solution. For your information, just first thing, it is not calculated practically. but second, it can be determined using this law. By the way, you study this class, and you are going to know about this class. Okay, and third very important point that when there are three interactions. When it is solid dissolved in a given solvent, then there will be a solid-solid interaction. There will be a solvent-solvent interaction, and there will be a solid-solvent interaction. So different interactions need some energy. Either they absorb the energy or evolve the energy. And the net results gives the enthalpy change during the formation of solution per mole. So we are going to study it in the next lecture. Very famous, that is the Bohr double cycle. Today we are going to stop here. Thank you very much.